Okay, good morning. Let me start actually, it should be second lecture, but I have to give this lecture for the second time because last time we have a big problem in the network. So let me start about the magnetic sensor. I just explained what is the meaning of the sensor in modern days. That means the sensor means we convert some oh just a moment. Okay. Yeah. In many cases we need to convert some physical or chemical quantity like temperature or field or pressure or the intensity of the light should convert to the some kind electrical signal. So in many sense, we convert some physical or chemical variation to convert electrical signal. We need some kind of interface that is called the sensor. So nowadays, that means this kind of connection between the real world to the digital world. After we convert the physical quantity or chemical quantity to the digital signal, the electrical signal, we can convert it to the digital. So then we can use this kind of number for many purposes. And there are many kind of sensors. And also, this cartoon is the screen capture of my old cellular phone, my old smartphone. App Store, you can find many apps if you search by the keyword of sensors. For example, in this screen, there are many kind of sensors in my smartphone. It may be Galaxy 4 or 6, some very old version, but still have the accelerator sensor, and magnetic sensor, gyroscope sensor, pressure sensor, and proximity sensor, and so more. And you can see here, 18 sensors are in single smartphone. And nowadays, the modern smartphone has even more sensors. And also, there are many apps which they are using the sensors, even though you didn't recognize it. And also, in a modern car, there are so many sensors and also many motors. And if you get a modern car or a new car, there are more sensors and more sensors. Especially for the self-driving one, there are a lot of sensors required. So there are many researches about the sensors, but we're going to focus about the magnetic sensors in our class. Okay, so far I explained the modern electronics and some kind of sensors very briefly. So the spintronics means we want to make something with the spins. Here the something means we want to make a better memories, which should be non-volatile and even faster and smaller and cheaper and using the less power and also keep the stable state. And also we want to make a better transistor and we want to make some kind of logic operation and even better sensors with the spins. That's the meaning of the spintronics. And in order to make such kind of devices with the spins, we have to manipulate and detect the spin state. That means we have to read and write the information by the spins. That's the goal of the spintronics. Okay. So, now are you guys all okay, or do you have a still problem sharing the screen? Okay. Just a moment. I'm gonna start another slideshow. Moment. So can you see the next slide? How about now? How about now? Can you see my screen? Can you see my slide? Okay. Okay, let me start again. In a second PowerPoint, I'm gonna talk about the magnetic memory, the history of the magnetic memory. In a previous class, I explained the meaning of this book. This is the meaning of the expansion of the data storage, and also there are many predictions about the desired the information storage capacity is over the available storage. So that means we need more and more storage, but this is easily understandable based on your personal experience. You may have some such kind of experience. If you take a lot of photos, you can already pull over your cellular phone memory or your hard disk drives. Then you can buy a new one. So this can be happens in the all around the world for everyone. So everyone wanna buy more memory and more memory. So that means this market, the future of this market is very bright. Okay, so let me start about the very old type of the data storage. Can you see this very small card? This is the name of punch card. As you see here, there are small dots and small black arrays and white arrays. The white array means there is some kind of holes. This can be made by this machine called the puncher. It's like a typewriter. This guy types some command, and this is the kind of piece of paper card. So the machine makes some holes for each point. So then actually this is the kind of the represent kind of alphabet. So at that time, the punch, this guy, the job of this guy's name is Puncher. So there are many predictions. The punch is the very promising job in the future. So this is very funny because this job is actually disappeared after maybe 10 years something. So that means such kind of future prediction is very not easy. It's easily incorrect. So for the student, nowadays many people predict some job is good for the future, but it's you cannot believe it. So anyway, so this box is the kind of a single program. In this box, there are many this kind of punch card, and they represent like a 1,000 lines of the code. So at that time, they stored this little program code in this box. And in the right panel, there are some kind of drums. And in this surface of drums, they stored some information like this. So they are rotating these drums and read the stored information by serially. So can you imagine how much memory for these machines? It should be very small. Even you can store the single book in this kind of large machines at that time. And the next one is magnetic tape. As you see here, there are large reels with the magnetic tapes, and this is a video cassette tape. Probably the young student never see such kind of video tapes. And in a right panel, this is the small music player with cassette tape called the Walkman. This is the one of the popular machine about 30 or 40 years ago. And here, the one audio tapes. Usually we can store the 1-hour song in this kind of magnetic tapes. That means if you convert it to the MP3 file, it's like a 16 megabyte, something like that. But this is this storage is analog, not the digital one, so you cannot say the one-to-one correspondence. But you can usually imagine the amount of the data stored in this tape by the time of the song. And in the right bottom panel, you can see the backside of the credit card. And this disk is the kind of the image viewer of the magnetic stored image. Just a moment. Yeah, I'm gonna verify. As you see here, there are small strips. You can see this kind of magnetic image by this small equipment. Actually, I have this one. So if we have a offline class, I'm gonna show this one. And this photo is very special one because I took this photo by myself when I visit some museum. At that time, this machine is called the Univac. It's very old style machine, and they including such kind of magnetic memory. So it's very it was very interesting for me. Okay, and how about the magnet? Everybody using the magnet in every day, and there are many magnets around our common life. And if you say the magnet, you can easily imagine such kind of a horseshoe type magnet. And this kind of magnet is usually made by aluminum, nickel, cobalt alloy. So we call this is a alico magnet. And also there are many such kind of magnet, looks like very dark, the black, and they are usually made by the ferrite. It's a kind of iron oxide. Iron oxide is one of the material in Earth, so it's very cheap. But this kind of magnet is for the performance is not so good. And there are many magnets you can easily find in your refrigerator, and they actually even in this simple magnet, the details of the magnet structure is quite complex. As you see here, there are small arrow represents the direction of the magnetization of this magnet, and as you see here, there are up and down magnets. The reason we made such kind of complex structure is to enhance the attached force, the repellent magnet, to the metal surface. You may understand the structure of this domain in near future. Okay, and this is also the domain image by some magnetic ferrofluid films. With this kind of film, you can easily see the domain structure. And there are another type of magnet called the anti-ion boron. And this anti-ion boron looks like very bright, and the color of this anti-ion boron magnet is quite different to this ferrite magnet. The ferrite magnet is usually very black, and this one is like a silver. And this anti-ion boron magnet is very strong. So you can see, just a moment. I don't know, you can see this image or not. Just a moment. Okay, so I'm gonna show this slide, then you may click this one, or just a moment. Let me. Yeah, I wanna show this video clips, but it's not easy. So you may watch this clips by yourself after this lecture. Okay. Okay. And there are magnetic data storage called the floppy disk. I think you guys see such kind of a disk, and also, original version of a floppy disk is a very large size, like this one. So this is the size of the like a medium size of pizza, very large one, and it's getting smaller and smaller. But the capacity of the data is getting larger and larger because we can increase the density of the data. And also there was called the zip drive, and in this time, this single drive have about 100 megabyte, and at that time there's a huge memory. But this machine is disappeared after the capacity of the data is increased. Okay, and how can we store and read the data? For example, in a magnetic tape, there is this is the, let's see, this is kind of a tape, and in a tape we made a very small magnetic particles. We painted the very small magnetic particles, and we aligned the magnetic particles direction, magnetization direction by this shape, NNS or N to S. So in the N to N case, there are a huge stray field. There are many fields starting from the N to S, from the N to S. So there are many very strong magnetic field here, and in upward direction. And in this S to S, there is some downward field. So when we read the magnetic field in this surface, we obtain such kind of peaks. And we can convert it to the digital output corresponding to 1, 0, 0, 1, 0, 1, something like this. So in this idea, we can store digital information in a magnetic surface. Then how can we increase the density? That means we have to make the smaller bit size, smaller pattern size. Then we can increase the data intensity. But if you decrease this size, the stray field is getting smaller and smaller. So that means we need a better read head. We need more sensitive sensor. Okay, so as you see here in a credit card, you know there are some magnetic strips. So if you use the credit card long time, sometimes it's not working. So we lost the information in the magnetic strip. And as you see here, even in the magnetic strip, there are many informations. So there are 3 tracks. One is the card number and the name of your the card holder and the expiration date. And also there are another information is stored in many places. But nowadays, every credit card has some kind of RF chips. So it's getting the magnetic strip. The usage magnetic strip is not that important, but still we are using it. And if you take a look the this magnetic strip, there are many small bars. This is called magnetic domain. And as you see here, they are corresponding to 1 or 0, and you can see the digital information stored in this strip. And this can be converted to this signal when you read it, when you read the magnetic strip by the magnetic reader. And also nowadays, many people using the Samsung Pay. And inside of this smartphone, we have small coils. So they can generate magnetic field, and this magnetic field sensor read it. And nowadays, everybody using the hard disk drive. In a hard disk drive, this is the real image of the hard disk drive, actually TM image. And as you see here, there are many small grains. There are some black and white, and between 2 grains, there is a white one. The white one is the so-called grain boundary. And when we store the information in this surface by the magnetic field, the magnetization of this area, let's say this is the up region, and this is called the down one, up and down. And you can easily see we can distinguish this up and down domain by assigning the number 1 or 0. So we can store the digital image in this shape. And as you see here, if you make this grain size getting smaller and smaller, we can make a more fine information, more fine boundary here. So that means if you want to store more smaller information, or dense information, you should make even smaller grains. But there are many limitations. So that's why we are still keep going to improve the performance of the hard disk drive. So anyway, as you see here, this is the 15 nanometer scale. So this single grain size is order of around even is less than 10 nanometer. So if you make an even smaller grain, there are some kind of problem called the super paramagnetic. We're gonna learn about this anyway. So in a modern hard disk drive, we used this kind of technique, and in the left panel, this grain can be converted by the small magnet N to S. And if we want to write the information here, we need some kind of coil and generate magnetic field, something like this. So you can convert to N is at the surface or S is at the surface. And also you can read the strip field from this magnetic surface by the magnetic field read sensor. And we're gonna learn about the GMR and TMR in maybe next class. But this is kind of a magnetic sensor. That's enough now. And in order to access the data, you may see this is the old style music player. And you may know this record player. We call this turntable because this is rotating. And this is the kind of read sensor. This arm is moving around this way. So because of this disk is rotating and this head is moving radially, we can access any place of this surface by sequentially. And it's quite same to the hard disk drive. In a hard disk drive, there is some rotating plate called the plater. And we have such kind of lead arms, and they are moving around this radical direction. So we can access any place in a disk surface. And if you take a look more carefully, there is some multiple stacks called, this is the plater. So for each surface of the single plater, we have a read head, and there are many read head. Like if you have a single plater, we have a two read head for front and the back side. And if you have a two plater, then you have a four head, and so on. So this hard disk drive operation principle is quite similar to this old style turntable. And let's take a look more carefully. Before that, this is the very old style hard disk drive, and as you see here, there are many platers. And this is the mechanical arms. They are moving. There are some arms inside of this machine. And this large machine is first version of hard disk drive, and at 1976 it was commercialized first, and the cost at that time is as you see $50,000, and the capacity of this hard disk drive is about 5 megabytes. So if you want to store your MP3 file, your favorite music, you cannot store a single song in this machine. And just imagine this $50,000 at that time is really huge money. Maybe you can buy several cars with this amount of money, but you can store only this amount. And there are a lot of progress of the hard disk drive development. This is the very small version of a hard disk drive, and you can store about at the time maybe 10 gigabytes something. I don't remember exact number. And this is, I already showed this one in our last class. I'm going to skip it. And let's take a look more details of the hard disk drive. In this left panel, I already explained the plater and the disks, the arms. But if you take a look more closely with the better version of the hard disk drive, this is the kind of anatomy of the hard disk drive. And this is the plater, and there is the read head, and several read head, and there are some actuator and so on. Okay, so this is the animation I took from some company, and now you can understand what's the meaning of this yellow disc. This is what I call the plater, and there is some read head. And if you zoom in, yeah, there is some kind of this is the kind of coil, and this is the read head. And if you take a look more closely, we have a magnetic sensor. So in this yellow surface, we have a stored image, stored information, and this they are now rotating. So the bottom surface is moving, and as you see here, the magnetization direction of this material is changed because of the magnetic field from this surface, disk surface. So when they change the direction, the signal is changed because this is kind of magnetic sensor. This is called the MR head, the magneto-resonance head. Because this material is designed, they change the resistance by the magnetic field. And if you made some different materials, we call this is the GMR, called the GMR. And there are many layers. I'm going to explain more details about this later. And one part of this material, one part of this device, the magnetization direction is rotating very easily, and we have a getting better signal. That's what we call the, this is a giant magnetic resistance, because this stack is designed to generate a large magnetic resistance. Okay. Okay, so what happens in this GMR sensor? They are consist by 4 layers, and for each layer we have they are all materials, and also they are metallic. So there is some moving charge, and when they are parallel, the magnetization direction is parallel. The charge is moving very easily. But when the magnetization direction is a little bit changed, there are more scattering. And even they are anti-parallel, there are more and more scattering. So that means the resistance increase. That's a very simple idea. Okay, so I'm gonna explain the basic of the GMR, maybe next class. And there are another type of the magnetic memory called the magnetic main memory. And in this machine, there are many small plates, and this is the zoom of the this plate. And as you see here, there is some kind of a link. This is a magnetic link made by the ferrite. And there is a wire. It's like a net. So the magnetization direction of this link can be changed by these 2 wires. When you sending the current, there is some kind of magnetic field generated by this current, and you can assign the direction of magnetization of these links. This is called the magnetic core memory, and they are used to the main memory of the computer system at the time. So nowadays the silicon memory is the mainstream, but before the silicon memory, people used this magnetic core memory. And this is the actually real photo of this kind of core memory. And I really ask the student, please remember the shape of this memory, because this is basically same to the modern memory architecture. Even we make the very small size of this type, but the basic idea is same. There is some kind of a cross of the lines, and the information is stored at the cross point. And also, this type of the memory, other name is LOL memory. LOL means the little old lady. So means when people made this kind of memory, it's made by the hand. Every ladies sit down and they made such kind of memory by hand. So this is the simple model of the core memory. And actually these 2 photos I also I took these photos by myself in a museum. So this is looks like very poor, but they are working at that time. And I'm gonna recall this view graph again. This is about the DRAM structure. As you see here, the main idea is the same. There are some kind of lines, and this direction called the uh, uh, word line and the bit line, and the information is stored at the cross point. They are all same idea. Okay. So there are many kind of memories, like DRAM I just explained, and many kind, like NAND flash, which one is the using USB drive and your cellular phone. And now we're gonna learn about the STT RAM. It's called the spin transfer torque RAM, which one is the magnetic memory. And there are other types of memory. And as you see here, there are many kind of categories. And as you see here, the DRAM, they have many good points, but some red one. And also flash memory, there are many good points, but there are many red part. And STT RAM, it looks like very promising. There are many advantages of this kind of magnetic memory, but there are many requirements in the future memory, like non-volatility, and it should be very fast, and it should be energy efficient. And this magnetic memory satisfies all these requirements. But still, there are many technical problems which one we have to solve in near future. So anyway, it's getting close to the commercialized, and actually there are some prototype of the managed memory is already in the market, even though you didn't recognize. Okay. So many part of our lecture is about this magnetic memory and how you can build up this memory and how you can read it, how you can write it, and how we can enhance the performance of this memory. That's the main part of my lecture. Okay. And I'm going to explain about the match sensor also, because the match sensor is very important in many applications. So some part of my lecture is about the match sensor, or the other word, some kind of MR sensor, because we have to convert the magnetic field to the electric signal. In that case, the magnetoresistance is very important. Okay, and also there are many advantages of the magnetic sensors, because the magnetic field sensor we don't need to contact the sensor to the some kind of material. Like for example, if you want to measure the temperature in water, you should dip your thermometer to the water. So you need direct contact. Many sensors require the direct contact, but in a magnetic sensor, we don't need many cases. We don't need direct contact. That's very big advantage. Okay, and for example, in a magnetic sensor, they are very robust to dust, and they can use it in a dirty environment. That's very important in the automotive applications. And so you can use this magnetic sensor to measure the speed and rotation and distance sensor or proximity sensor. And as I already emphasized, that non-contact is very important one, and the cost is very cheap. And there is a simple example of your smart cover with your smartphone. For example, this is the iPad with the smart cover. And as you see here, the cover, when you open the cover, the machine is wake up. And there is some kind of a mass sensor inside of this iPad. So they recognize the cover is up or not by the magnetic field. So if it is offline class, I'm gonna show such kind of behavior by magnets, but unfortunately I cannot show it. And as I already said, there is some rotation and distance sensor. For example, if you have some machine, which one is a rotating part, and if you have some magnet sensor here, and we have a magnet here, and with this small hole, the magnetic field from this magnet is disturbed. So they can detect this kind of a part by measuring the magnetic field. And also, we have such kind of gear. The magnetic field measuring in this magnet sensor is disturbed by the rotation of this gear. So this is one example. If you have a magnet and a field sensor, when the gear is close to here, there's a magnetic field looks like here. And if this part is coming, the magnetic field is changed. So you can measure it. So actually, in any kind of mechanics, you need some control, this kind of rotation. Then you have a magnetic field sensor. Because, as I already mentioned, in this magnet sensor, we don't need this part is very clean. If there is some dust and some kind of oil, but still this is working. But if we are using some, let's say, optical sensor, they are very weak for the dust, or if you cover up with some oils and some kind of lubricant, the optical sensor will be malfunctioned. And also, there is some kind of position sensor. This is the gear in an automobile, and with the position of the shift, you can detect the position of this shift bar by the magnetic sensor. So there are many magnetic sensors inside of any kind of machines, even though you didn't recognize it. And also, in any kind of mechanical machines, there are some kind of sensors, and you should control it, and you need some kind of feedback in any kind of mechanical control part. So sensor is very important in many applications. And for example, this view graph I borrowed from the company name of Infineon, which one is one of the most largest industry in automotive markets. So there are many kind of sensors. As you already explained, there is some rotation speed sensing. So they need the field speed sensor and transmission sensor, and even for the very simple one, the window lift, you need also sensors. And also for the position sensors, you need rotor position, steering angle sensors, torque sensors, and contact list switch. There are many things. They are all related with the magnetic sensors. And you can easily see the in a CAD CAM, there are control the rotation is very important. And also in a brake system, ABS brake system, you need also some kind of sensors. Then what kind of magnetic sensors are using in industry? Most popular one is the Hall effect sensor. I'm gonna explain what is the Hall effect again. But anyway, there is some kind of Hall effect sensor, and the GMR, which one I already mentioned, the giant magnetic resistance sensors, and also there are AMR. AMR is the anomalous MR, and TMR is tunneling MR. So you can easily recognize there are many MRs. The magnetic resistance means if you have some device which one is change this resistance by the magnetic field, we call this MR sensor. And there are many kind of MRs. Now I'm said just 3 types, but there are more. I think it's more than 10 types of the MRs. So I'm gonna explain this GMR, AMR, TMR in next lecture. Okay, so in this course, we're gonna learn about the very basic part of the multi-materials, and also we're gonna learn about the permanent magnets, and we're gonna about the transport, which one is very related to the spintronics, and Hall effect, AMR, GMR, TMR, which one I just mentioned before in the previous slide. And also, this is for the data storage and memory applications. And also, there are many in progress topics like spin transport torque, spin orbit torque, spin Hall effect, spin Seebeck effect, Rashba effect, and so on. There are many concurrent topics. I'm gonna touch it. Okay, I'm gonna skip this part. Okay, so I'm gonna repeat the speed of the this second level because I should finish this one in the last class. But okay, I think we're gonna have some time for the questions. Okay, now it's time for the questions. So please use the chatting message and give me questions. Okay, the question is, yeah, I think your question is about this photo. So your question is about why this one and this one has a different direction. Am I right? Yeah, I'm sorry. Actually, I didn't remember very details of this memory, but there is some reason. I'm gonna share some the website just a moment. Just a moment. Okay, so I just update my slide. Can you see? Okay, here the this magnetic core memory is somewhat complex. As you see here, there is some the perpendicular one and the horizontal one, and also there is something more. We need more lines actually for the write and read. And actually in this modern memory like a DRAM, there is some also there is some hidden lines I didn't explain. Anyway, we need such kind of arrangement. For example, here, yeah, as you see here, there are more lines, not only the perpendicular and the horizontal one. Okay, and for the Samsung Pay, okay. Okay. Can you see some web page? Okay, so okay, this is about the kind of Samsung Pay, and I took this photo from this website, for example. So I believe this is the real size. So I don't know really they are using this size of coils, but somehow they made such kind of things. So you may Google it easily. I used the keyword of the Samsung Pay coil, Google. Okay. Okay. So ask more questions. Okay. Good questions, 동률. Actually, the equipment I showed you today is called ferrofluid films. In this equipment, you have a very tiny size of the ferromagnetic fluid, which one is freely arranged, moving inside of very thin films. So they aligned the direction of the magnetic field. So we can see the domain, but there is very poor resolution. They have only like a millimeter size of the resolution. But with the core effect, as you see, if you are using the microscope, you can see the micrometer size. So this ferrofluid film is very rough measurement. You cannot see very small size of domain. And I have a DC equipment in my office, so please come to my office to take a look how it works. Yeah, if it is offline class, I will bring this equipment in a class, then I'll show this thing to all students. But yeah, maybe if you have a offline class in April, I'm gonna bring it. Okay, so more questions? Okay, please think about some questions. Then before, at the meantime, I'm gonna show the YouTube things. Stolen. Yeah, this is about how the magnet, the Indian magnet is strong. Can you see? Okay, so you can see this large size of Indian magnet is very dangerous. When you handle it, you need extra caution. Otherwise, you hit the magnet and you got some damage in your fingers and hand very easily. So very you need some extra caution. I'm sorry. I just accidentally exit the sessions. Okay. So, please ask more questions. Yeah, this question is kind of, okay. Just a moment. Ah, okay. So, next class, maybe just a moment. Not next class, but maybe uh, yeah, after 2 weeks, I'm gonna give a very details of this GMR. So now it's not easy to understand, but just remember that what is the meaning of the GMR? That's the very large MR, some kind of very uh, technically well-designed structure to generate large MR. That's the meaning of GMR. And I'm gonna explain very detailed physics in next lecture. So not next, but maybe 2 weeks or 3 weeks after. Is okay? And also, at the meantime, you may Google it. Then you can find very detailed information also. Yeah, nowadays, if you have any questions, you can find in the web, actually. Yeah, please ask more questions, other students. Okay, it's good questions. Any kind of sensors are sensitive or insensitive to the temperature. So, for example, holy pad is very, very sensitive on the temperature, but MR sensor, magnetic MR sensor, is relatively less sensitive. So, in sometimes temperature sensitive sensor is good, some kind of application, and in other kind of application, the temperature insensitive sensor is better. So it depends on the purpose. But in order to understand the temperature dependence, you should understand the basic principle of each sensors. So if you need a temperature insensitive application, you should find such kind of sensors. And also, if you want temperature sensitive sensors, you can find something, yeah, another one. Other questions? Yeah, I recorded these chattings. That means I recorded your all questions. So if some student didn't ask any questions, then you're gonna have a problem. Please ask any questions. This is kind of mandatory requirement. iPad or Galaxy Tab, they are usually using the Hall sensor. But some of them are using GMI sensors, but Hall sensor is more popular because it's even cheaper and we don't need a very large, very sensitivity. I mean, you don't need to measure the very fine field. This application, you can get there is money field or not. So it's much easy. Or you don't need a very expensive sensor. So usually they're using the Hall sensors. And also, if you find any kind of app, keyword of sensors, you can download it and you can see what kind of sensors in your smartphone, which one I already showed you. Then there are very details of the information of sensors, which company made it, and what kind of sensors. So you can find in sensors in your smartphone. Oh, that's good questions. Actually, there are many mechanisms of the MR. Actually, that's the one of the main part of my lecture. I'm gonna explain what kind of behind of the physics in the such kind of MR effect, and I'm gonna give such lecture maybe 2 weeks later. Yeah. So actually, as I already explained, there are many kind of MRs, and each MR has a little bit different physical origin, but there are many common parts also. So somehow the transport, the motion of electron is affected by the magnetic field. That's the source of the MR. Okay. I'm going to explain the magnetic memory, and basically they are very very similar to this LOL memory because they write the magnetic information by the these cross patterns and read it also some read line, and there are many common points. But this LOL memory size is like a order of millimeter, but we are playing with the size of tens of nanometer. That's only the different point. Yeah, actually, the very details, there are many differences in the very details, but the this cross point geometry itself is still common. That's the point. So it's like just a downsizing of this old style memory. Yeah, actually, Changa's question is also the main part of my talk, and I'm gonna explain it maybe 2 or 3 weeks later. Yeah. Please keep your curious about these questions. Okay. Okay, so I think it's time's up. So today's we have still little problems, but so far it seems not so bad. Okay, so I'm gonna close this session, today's session, and see you in Wednesday. And if you have any questions related to this today's lecture, or anything, you may ask to questions by the email or KakaoTalk. And also, I want to upload these two PowerPoint files in the LMS. Please download it if you want. Okay, then see you Wednesday. Bye.